So today we're going to talk about 5.5, which is the substitution rule. So we're going to use something called U sub or U substitution. Basically, this is, so you guys have learned that the integral is basically a way to find the antiderivative or another name for the antiderivative. So we've learned that you can use integration on plussing, adding and subtracting terms. We've learned that you can use integration on multiple functions, but the one thing that would be hard for us is to do integration on a function that is embedded within another function. So think back to when you learned the chain rule, when you learned composition of functions. You found that there'd be some function f of x, and then someone would go and take a g of x and plug it inside the f of x, so it would make a composition. So you learned how to do the chain rule to deal with a function embedded within another function. So if we're going to find out how to do antiderivatives and how to integrate, we need to find a way to deal with functions within other functions. So what our method will be is U substitution. This will be the hardest integration technique we learn in this class. Those of you that take Calc 2, you'll start right off with more integration techniques. That'll be one of the first things you talk about. But for us, this will be the most difficult section. So in case you were not able to attend the lecture on this, I'm going to go ahead and make this video, okay? So basically, let's start off by working with somewhat of an easier example. So let's say I ask you to find the integral of the cosine of 3x dx, okay? And remember, the whole point of, or I shouldn't say the whole point, but a way that you can check your integration to see if you're right is by taking the derivative of your answer, and you should get back to the original, okay? So we could say, well, I know that the derivative of cosine is sine, so then I feel like the antiderivative of cosine would be sine, and then we would say 3x, right, plus c. So this is what we think our antiderivative would be, because I know if I differentiate sine, I get cosine, okay? So let's take a minute. Let's just check this. Let's d dx sine 3x plus c, okay? So we're going to d dx this. All right, so we're going to get, let's see, cosine 3x plus 0, so oops, plus 0. We don't even need it, so we're not going to write that. And now we have to attach the derivative of the inner function by the chain rule. The chain rule says, well, the derivative of 3x is 3. So notice this is not identical to this, and that's what you need. You need it to be exactly the same. So what do I need to do? Well, I need to somehow get rid of this 3, right? So I could divide by 3. Okay, so this would be the derivative. So what if I said this 1/3 sine 3x? Now let's try this again, and let's see. Let's do the derivative of sine 1/3 sine 3x. Well, 1/3, let's say that this is our antiderivative. Let's say that is our answer, okay? So we want to check this by doing d dx of 1/3 sine 3x plus c. So when we take the derivative of this, we're going to get 1/3 cosine 3x. Now the chain rule says we have to take the derivative of the inner function, which is times 3, right? Okay, times 3, and then plus 0, right? Because the derivative of a constant is 0. So now the 3's cancel, and we're left with cosine of 3x. And look what we have right here, cosine of 3x. So this would work. So we found our antiderivative. All of this right here, you guys, is just a check. All we're doing is to check to see if our answer works. It's not actually required in integration, but it's a good thing to know that that is the relationship between integration and derivatives, okay? So that would be our answer, and we'd be done. But that's, you know, you guys see this was a pretty easy problem, so I could guess and kind of manipulate it and everything. So what we want, I mean, technically in the long run, you could do this for every problem and just keep messing with it until you take the derivative and get back to where you start. But it would start getting out of hand and become very difficult, okay? So what we do instead is we try to say, well, what I'm going to do is I'm going to let u equal 3x. I'm going to let the u be the inner function. Let u be the inner function, okay? Sometimes they call it g of x, all right? Okay. Now, when we take the derivative of this, I'm going to d dx both sides, and this will become du dx equals 3. Okay. Now I'm going to separate the du and the dx. I'm going to move the dx over to the other side. So now we will have du, oops, sorry about that, du equals 3 dx. So if you notice, oops, right here I have a dx, right here I have a dx, but what's in the way is the 3. So I'm going to divide both sides by 3. And so now I have 1/3 du is worth a dx. So this is the direct substitution, okay? I'm going to be able to take, everywhere I see a dx, I can rewrite it as a 1/3 du. So I'm going to come up here. I'm going to put a 1/3 du right there, okay? Right here, you see how I said that 3x was worth a u? I'm going to put the u right there. So now let's look at our integral. So our new integral is the integral of the cosine of u times 1/3 du, right? But we know that this is a constant, so we can move any constant out in front when it's being multiplied or divided into an integral. So this will just become cosine of u du, okay? Now we know that the antiderivative of cosine is sine of u plus c. So we just integrated, all right? We just did our job. However, nobody ever asked you to find out what the sine of the antiderivative of cosine of u was. They wanted to know the antiderivative with x's. So we now back substitute in. So this is 1/3 sine of 3x, because that's what our u used to be. And we have our answer. And this matches the one that we had guessed. Okay. So this is a lot of work. I went through a lot of extra steps. Some of this stuff, you guys, when you get better at this, you're going to skip these. I just wanted you to see that this is the like a solid concrete way to do this. Okay. Now, this is not how many people teach use substitution. Some people just say, well, what do you need to cancel the leftovers? So then they write that on the outside of the integral, okay? Or what do you need to cancel what the extra pieces are that you have with your dx? I choose to actually do the math right here. I like to show the actual algebra or whatever I need to do to make things work. So a couple things, okay? So some key points. Okay, so a few key points are, look for composition. To ID u, okay? Or a good u, let's say a good u, okay? Because you can pick u to be anything, but it may not work, okay? Now, so we look, then we say always replace dx. So always replace dx. And your dx must always be in the numerator, right? So I'll show it to you guys, but the something is, if you forget to write dx in your integrals, you're always going to have trouble with this type of integration because you're missing pieces, okay? And it'll really haunt you in Calc 2 if you don't write your dx. That's why I always told you that you have to write your dx, not only because I say so, but because it's required, okay? Then you have do your algebra carefully. So do algebra carefully. Remember, you don't want to make stuff up that are not actual rules of mathematics. Some students FOIL incorrectly, or they improperly square, or there's all kinds of things that students can do wrong. You guys got to be real careful with that, okay? Replace or back sub, replace u in the final answer. Don't forget to do this, otherwise you're not actually answering the question, okay? Okay. I think that'll do it. In general, you're trying to look for what u is embedded in, or you're trying to find a composition of functions, what function is embedded inside the other function. So a lot of times the focus will be the inner function, okay? So let's take a look at another one. Okay, I forgot to write that. Let me just add that to that. Okay. So let's look at this problem. Let's take the integral of 1 over 3 minus 4x dx. Okay, so now we're thinking, what was the original function before somebody messed with it and put another function inside of it? Now think about this. Doesn't this kind of look like 1 over x, but then somebody put a 3 minus 4x inside of that? So I'm going to let my u be 3 minus 4x, because if it was 1 over x, I know that that's the natural log of x as an integral, right? So I'm going to say, well, if I could just rewrite this as 1 over u, then I would know that this is the natural log of u, or the absolute value of u. So the thing is you're going to have to start learning that whatever you say your u is, now I'm not going to, you guys see how I went through and did all these steps. I'm going to kind of show you how I would do it just naturally, instead of trying to explain it per se like an instructor, but just as a student how I would do it. Now I'm going to say du is equal, so I'm going to take the derivative of both sides. And in my head, I'm already moving the dx over to the other side. So this would be negative 4 dx, okay? Now notice I have a dx here and I have a dx here, but I don't have this extra negative 4. So what I need to do is I need to divide by negative 4. Okay, so now as a student, this is how I would rewrite it. The integral of 1 over u, and now du times du over negative 4, right? These cancel. So I took this and I placed it for the dx, and I took this and I placed it for the 4x. I'm sorry. I took the u and I replaced it here. So now I have 1 over u, du negative 4, but you guys know that we can rewrite this as negative 1/4 integral 1 over u du. Well, the antiderivative of 1 over u is just ln of u, of the absolute value of u, plus c. But again, you cannot forget to substitute back in u. So this becomes the natural log of 3 minus 4x plus c. And that's our final answer, and we're good, okay? That is how you do u substitution, okay? And in general, u substitution takes a complicated looking integral and makes it simplistic. Notice how nice and easy that integral is. That's what you want to do, okay? So let's look at another one. So they sometimes start off looking terrible. So we could have a problem like this: square root of x, 1 plus square root of x squared, okay? So we have the integral of dx over the square root of x times 1 plus square root of x squared. Now, a lot of students, when they first see this, they say, okay, let me take the complicated part, 1 plus square root of x squared, okay? That's what normally happens, okay? Now think about this. What is the leftovers then? The dx over square root of x has to be what the du is. Remember, you get to take the derivative of this, and that has to be everything. So if I du this, I take the derivative of both sides, this would be 2 times 1 plus the square root of x times the inner function, which would be 1/2 x to the negative 1/2. Now look at this. That means that my du, I have to have all of this in the problem. Well, I do kind of see this part. I kind of see this part right here. This part looks pretty good because you see here, isn't that right here? However, what the heck am I going to do with all of this? This doesn't fit right. So what I have to do is I say I must have chosen the wrong u. I have too much. I have too many pieces to account for. I can't account for all of them. So what if I just say, let u be what's under the squared, 1 plus square root of x. Now when I take the derivative of that, I get 1/2 x to the negative 1/2 dx, right? But this is actually du equals 1 over 2 square roots of x dx. And again, I see this right here with this part right here. I feel pretty good about that. So I just got to get rid of that 2. No big deal. I'll just throw the 2 over here and cancel that 2. So now I can say that this is the integral, when I rewrite it, of 2 du over u squared, right? Because 2 du's are worth dx over the square root of x. So now this is actually 2 integral u to the negative 2 du. Now I can integrate it, and I just use my general power rule for integration. This would become 2 u to the negative 3, oops, I'm sorry, not negative 3, to the negative 1. I add 1 to the power and then divide by it, plus c. So this would be negative 2, but what did we say u was? We said that u was 1 plus the square root of x to the negative 1 plus c. Now that's a final answer, but if you're doing the homework online, they may be a little pickier, so you might have to do this. Right, you might do that, or I guess you don't need the parentheses in the denominator. So that might be something that you see. I would take this on an exam as an answer, but the homework might be a little bit pickier and take the bottom one, okay? So just be careful with that. Make sure you try to answer it how the homework asks, and it'll make it easier on both of us, okay? All right, so let's take a look at another one now. And now again, I also, before we move on, I want you guys to notice how complicated this problem looked at first. Like, how are you gonna guess that? Like, that's really hard, okay? So that's what USub can do. It can make our problems much simpler. That's the power of it, okay? Now let's take a look at something with limits of integration. So we're gonna have the integral from 0 to the square root of pi over 6, okay? Inside the square root, and this is of x sine 2x squared dx. So let's look at this problem. Now this one, once again, it's like it's a product and then there's a function within another function. So there's a lot of things happening here. So what would you estimate u to be? What would you guess u to be? It's either got to be sine of 2x squared, it's got to be x, or it's got to be 2x squared. You would, in general, not let x be u if you're doing u sub. Maybe in like integration by parts or something like that might happen, but not in this case. So we're going to say u is the inner function, which is 2x squared. Notice I'm looking what's inside the sign. That's kind of my go-to move, is to look what's inside of a trig function. If you're ever given a trig function, a lot of times u will be what's inside of it. Okay, so then du is equal to 4x dx. Now, hopefully you guys are starting to notice a pattern. You see how what we declared u to be had a power of 2 with the x, and then the outside would have a power of 1. That's normally when u sub is going to work nicely, is when the powers are off by one smaller than the other. Because whenever you differentiate and you're dealing with just a polynomial or something, your power is just going to decrease. When you start getting to e to the x's and stuff, things change a little bit. With natural logs, things change a little bit. But if you can notice that whatever you say u is going to be is the leftovers 1 power smaller. Again, this is just a general idea. It doesn't always work, but you want to think ahead of the game. Whatever you say u is, the derivative better be what's left behind, okay? So we see that it kind of is, except for we have this little 4, so we're going to divide by 4. So now we can say the integral of sine u times du over 4. So I can take that out. Now, in general, I want you to notice something. These limits of integrations are meant for x's, right? These are all dx, right? These are all x's. But we're now working with u, right? We now have u. So we need to have some limits of integration that will go with u, okay? So when you're doing a definite integral, you have 2 ways to do it. You can do it just like I did before, where we back substitute in for u, so we're going to plug our x's back in. Or you can change the limits of integration to match the u's, and you don't have to back substitute. So what I could do down here is I could say, well, u equals 2 times x, but what is x if we use this limits of integration? That'd be 0, so that means u is 0. And then we could say u equals 2 times x, but this would be the square root of pi over 6 squared, right? That's what, well, I guess I could write it like this, right? Because we're dealing with 2x squared right there. So I could plug that in and I would get what? 2 pi over 6. No, yeah, that's right, because it's in the square root. So we get pi over 3. So then my new limits of integration, if I want to stick to using u, would be 0 to pi over 3. 0 to pi over 3. And all I did was I took my limits of integration and I plugged them in for x. And I found 2 new u values. This means that you don't have to plug x back in if you don't want to, okay? Now, if you want to plug x back in and you can use the original limits of integration, you can, no problem. But remember, then you have to plug x back in. So I'm going to show you what the book wants you to do, but it works both ways. I've been doing it both ways my whole life, and it's fine. I've never run into trouble doing it either way. So this will be 1/4 sine, oops, we got to find the antiderivative. 1/4 times the antiderivative of sine, which would be cosine of u. Now we're not going to use the plus c because this is a definite integral and you don't use plus c on definite integrals. So this would be 1/4 and then the cosine of pi over 3 minus the cosine of 0, f of b minus f of a. So this would be 1/4 times cosine of pi thirds should be 1/2, right? And then minus the cosine of 0 is 1. So we should get what? Negative 1/2 times 1/4 would be negative 1/8. Does that sound right? I feel like I messed up somewhere. I feel like, oh, you guys see what I did wrong? This has to be negative. Because if we come back up here, I totally forgot I was doing so many derivatives in my head, which happens a lot with u sub actually, because over here we're doing derivatives, but over here we're integrating. So our minds kind of jump, and I just did it right now. The antiderivative of sine is actually negative cosine, right? Because the derivative of cosine would be negative sine, and this is not a negative sign up here. So I have to put a negative in front of it. So that's my mistake. So this will actually be negative, and this will be positive. And then this will be negative 1/2 plus 1, and that'll be positive 1/8. Yeah, there we go. So that's our final answer. Sorry about that, you guys. I did a common mistake. Probably better that you see it happen so you don't feel bad when you do it, but you just got to kind of practice and practice so you don't do it very often. Okay? So let's see what we got here. Let's try a much, much harder problem. This is one of the hardest problems you'll see in this course. So we're going to take the integral from 1 to 3. You know what? I'll just do the regular indefinite integral. And this will be x square root of 5 minus x dx. Now, I already know something's wrong. I already know I'm worried because u sub's not going to work very well. Because if I make this inside portion my u, what's the derivative of x? It's just plain old 1 dx or negative 1 dx. I still have an extra x outside. So I'm not going to be able to account for that x, but I'm just going to give it a shot because I know I don't really have anything else to work with right now. So I'm going to say u equals 5 minus x. That's the embedded function. That's the function within the other function. And then the derivative of both sides would be negative dx. So then I'm going to divide both sides by negative 1 by negative 1. So then when I go to rewrite this, I have the integral of x, and then I know that this is u to the 1/2 power, right? Because it's u square root of u. And then I know that this is negative du, right? So let me clean this up. This will become negative x u to the 1/2 du. So these guys are great. This is perfect. But this is bad news. I cannot have that x right there. I got to figure out a way to replace that. But this is what makes this a harder problem. This is called u sub with change of variable normally. I've also heard other teachers just call it u sub, but I call it u sub with change of variable because this needs to be accounted for, and the u sub does not immediately account for it. But remember, we made up a rule. We said that u is worth 5 minus x. So if u is worth that, I should be able to solve that equation for x. So I'm going to move x to the other side and move u's to the other side. So this will become x equals 5 minus u. I now have a substitution that I can plug right there. So this is what makes it much harder. You definitely are going to think, you have to think more on these. So this will become negative 5 minus u times u to the 1/2 du. Now I still can't integrate this, but what I can do is I can do my algebra. So this will be 5u to the 1/2 minus u to the 3/2 du. So now I have two terms that I can integrate piece by piece. So this will become negative. Now the integral of 5u to the 1/2 is 5u to the 3/2 divided by 3/2 minus u to the 5/2 divided by 5/2. Remember, I'm just using the power rule, plus c. So this will become negative 10 over 3 u to the 3/2 plus 2/5 u to the 5/2 plus c. Now that would technically be the answer, but nobody ever asked us to work with u's. That was a decision we made. So now we have to go back in and plug in our u. And we said that u was worth 5 minus x to the 3/2 power plus 2/5 5 minus x to the 5/2 power plus c. And that would be our final answer. Oops, let me clean this up real quick. And that would be our final answer. And this would be one of the hardest problems you will see in the homework. This is called U sub with a change of variable. You got to be careful of these. Normally you can recognize them, that you plug in your U sub, and then whatever you kind of visualize the du to be, it doesn't quite account for everything. Now again, du doesn't always have to account for everything, especially in terms of constants. But if it's an extra variable floating around, or an extra square root of x, or x plus 5 or something, you got to be more careful. That means the U sub won't directly work, and you might have to try something else. And then even after that, normally you still have to do some foiling or something like up here. So this is definitely a problem to worry about. This is a much more difficult problem than the standard. So let's look at a few more. Let me see if I have another one. Okay, this one looks tough. Let's try this one. X cubed 3 plus x squared to the 5th dx. Now I don't have this one worked out, so we're going to try to figure this one out together. Hopefully I don't make any silly mistakes and have to go backtrack and figure it out. So we have 3 plus x squared to the 5th times x cubed. So I don't feel like taking 3 plus x squared and writing it out as a polynomial and then distributing the x cubed to it. So I'm going to use U substitution. So I'm going to say let u equal the inner function, and I feel like that's got to be 3 plus x squared. But when I do that, I automatically notice we're in trouble, because this is 2x dx, and I have an x cubed here that needs to be accounted for, and I don't have it. You guys see that? That's the problem. And then, so I'm going to divide this by 2 and divide this by 2, and this is the best I can get. I got du over 2 equals x dx, okay? So what I'm going to do is I'm going to try to say, okay, now I know how to do U sub with change of variable. Maybe I can account for this a different way. So I'm going to say this is x squared times 3 minus x squared, plus x squared to the 5th. Now remember, this used to be an x cubed. I'm going to save one of those x's and write it over here, dx. Now, in case you think I did anything crazy, what is x times x squared? It's x cubed. I haven't done anything. I just wrote it separate. But it's still, if I multiplied this out and cleaned it up, I would still have an x cubed in front. But the reason I did that is, you see here, I'm saying that a dx, an x dx is worth a du over 2. And right here I have an x dx and it's worth a du over 2. Here I have a u. So I have my u here and I have my du over 2, right? That doesn't, I tried to use a highlighter, but it doesn't work. Okay, so this will be my u to the 5th, and this will be my du over 2. But I still have not accounted for the x squared. So what I could do is I could do a little scratch work, and I could say, well, or I guess I don't even have to do scratch work. I could just try to plug in what I know. So I'm going to say that this will become u to the 5th du over 2. And instead of, I said, I could solve for x squared right here. Couldn't I just say that x squared, couldn't I just say that x squared is equal to u minus 3? So then all I'm going to do is I'm going to take this guy and I'm going to put a u minus, I'll use green still, a u minus 3 right here. Remember, that used to be x squared, but I solved for x squared and found that it's worth a u minus 3. So now I have to distribute just like I did in the previous problem, and this in general is the way to go. So this will become u to the 7th over 7 plus 3u to the 6th over 6. Let me put the 1/2 outside. 1/2 out. You know what? I kind of skipped some steps. Let me clean this up a little bit for you guys. So this will become 1/2 integral u to the 6th minus 3u to the 5th du. Okay. Now I've seen some students think that because when they distributed, the powers went up by 1, but that's just because you were multiplying by u. So now we have to do 1/2 the integral of u to the 6th minus 3u to the 5th. So we got to find out, well, this is u to the 7th over 7 minus 3u to the 6th over 6 plus c. You could technically keep the c inside, but then what's 1/2 of c? Just some new c, so don't stress about it. If you want, I could do that. I'll just write it for you guys, plus c. And then this will become, what did we say u was? We said u was worth 3 plus x squared. So I'm going to say this is 1/2 times 3 plus x squared to the 7th over 7 minus 3 plus x squared to the 6th over, now these cancel and become 2, plus c. So this would be our final answer. Okay, so this is how you can do u sub with change of variable. It's a very, I guess it's very substitution based. It's very reliant on you understanding that you made up this first rule. You made up this rule that u was worth this. So you could just as easily say, well, if u's worth that, well, then x squared has to be worth that. And you don't have to write this step over here that I did. You guys don't have to write this step right here. This was just so you guys could see what I do. A lot of people will just write this step. They'll just jump straight to that, okay? But I'm gonna end the video. I didn't wanna make it too long. I just wanted to give you guys a follow-up to u sub. So u substitution with change of variable is normally the hardest part. Normal u substitution is hard also because you take like this really complicated problem and you make it simplistic, and that takes, you kind of have to eyeball it. You have to say, well, if I make this u, then what would du be? So that's something you guys really have to think ahead on. All right, you guys, that's going to do it for this video. I will see you in the next one for 6.1, area between two curves.